These are the projectile motion homework solutions. They're also solved on the physics classroom, but hopefully this gives you a little bit better insight. So a lot of the first six were fairly similar because they're horizontally launched projectiles. And that's because I think that's the most important parts for us to know. Um, if you were taking a higher level physics course or in a second year or something like that, we learn a little bit more about the angle launched ones. At any rate, this problem has something launched at 26 meters per second. I think it's a stone being skipped at 0.45 meters above the ground, above the water, I guess. And you're asked to find how far it goes before it hits the water. Well, this is a horizontal speed, and that doesn't change. There is no vertical speed initially, but it does start falling, so it'll speed up vertically. So to figure out this distance, we really need to know the time of the fall, because for horizontal displacement, we need horizontal speed, which we've got. We also need the time. So to think about the time, I need to think vertically. So this is an equation I can use when we start from rest, and vertical motion initially is at rest, or 0. So this is the height, 1/2, gravity's acceleration, time squared. So I rearrange that, take the square root, and I get a time of 0.3 seconds. Now, I multiply that by the horizontal velocity, and it tells me this distance is 7.9 meters. PC22 is very similar at the beginning to PC21. So we've got someone, I think it's Matthew Wattros, running off here at 4.6 meters per second, 2.3 meter fall. So to find the time of the fall, we'd use this equation again, starting from rest, so no initial velocity here. And I think I showed you a couple more steps about how I got time. So 2.3 on the left, half times 9.8 is 4.9 on the right. Divide that out, take the square root, get 0.69 seconds. So for part B, again, I rearrange this general formula, which is for horizontal motion. That's what the subscript h stands for. And I get that it's 3.16 meters is how far it goes. So that would be this distance here away from the side. So I would do something like this. That's that distance. So that's 3.16 meters. Now, we want to find the final speed. I told you this was a little bit tougher. I gave you some hints on that. So the 4.6 meters per second horizontally doesn't change. I need to find the final vertical speed. You could do that a couple ways. I did it this way. Final speed equals initial speed plus acceleration times time. I guess I should say velocities here. And that gets me 6.76 meters per second, vertically downward. So now this resultant is 8.2 meters per second because it's the overall speed. Some of the speed is horizontal, some is vertical, but that's the result. For 23, it's a pumpkin being chucked, pumpkin chunkin'. So this is going to be very similar to the first two problems. First, find the time to fall. That's fantastic, Adobe Flash Player. First, find the time to fall, and then that's 1.46 seconds. And now the difference is at this point, I'm given this horizontal distance. I'm not given the launch speed. So I use this general equation, but I know this position. I know the time from up above, so I can find the launch speed is 9.2 meters per second. So we're kind of working backward to get this. PC24, similar to number 23 and actually 21. So, actually, no, this is similar to 23. So, find the time, same way we've done before with the vertical information. Now use this position, the time, get the horizontal speed. For number 26, here we're given the horizontal speed. We know the height. We don't know this distance. But we're actually asked to find the time to fall here. And again, same way we've done before. Now we find the horizontal distance. Same way we've done before. So horizontal speed times time. This was very similar to 22C. So now I want to get the final speed. That's constant. Horizontal speed is constant with projectiles. The vertical speed is speeding up. So I use that acceleration times time formula, and I get that vertical speed down. And so it's basically the resultant of those, 4.86 meters per second. 27 is the final one where we're launched horizontally. So it's a little different because now we're trying to find the table height. Here we know the horizontal speed, and we know the horizontal distance. So if we know those two things, I'm going to find my time using a horizontal equation. So that's the general equation for horizontal motion because there's no acceleration. Then I rearrange it to find the time it takes to get to the ground. So that's a little algebra. It's about 0.46 seconds. And now I use this to find the table height. So it's the same equations we've been using before, just rearranged. So this is about a 1.05 meter table height. PC 28 and 29 are the ones that are launched at angles. So this is 28. And I drew a picture. I drew a triangle. I split it up into vertical and horizontal components. So for this, you're going to need trigonometry. So vertical velocity over the overall velocity is opposite over hypotenuse, so that's a sine function. Horizontal velocity over overall velocity is adjacent over hypotenuse, that's a cosine function. So get the horizontal speed, 6.98, vertical speed initially is 4.03. Now the horizontal speed will stay the same. The vertical speed is going to change at a very known rate of 9.8 meters per second squared. So, and we know at the tippy top of that path, the vertical speed is 0. So I can use this and rearrange it to figure out the time it takes to get to the tippy top. So initial speed upward, final speed at the tippy top, rate of change of speed is my acceleration, and I get 4.41 seconds up to the top. So the top time up plus the time down is the total time, that's 0.82 seconds. Once I know the total time, I just do what I've done before with horizontal equation to figure out the total distance it goes. So you're in the air for a total of this 0.82 seconds. It's moving horizontally, the speed we figured out earlier. So multiply those two together and you get the horizontal distance delta x. And it's purple on here, purple on here. To find the maximum height, we would need to find the distance that the egg drops during the second half of the trip, or that it raises during the first half of the trip, but I think mathematically this is a little easier to think about the second half because we know that the initial velocity vertically is 0 here, so we can use this version of this equation. So 1/2 9.8, half the time squared because it reaches its peak after half the time it's been in the air. And that's coincidentally 0.82 meters. So that's just somewhat of a coincidence. It's that time and that distance. It's a little unfortunate. The final problem, so once again I'm going to find the horizontal and vertical components of my angle launch projectile. Then about 20 meters per second up, 28.8 meters per second sideways. Use the same trig functions I used before. So time up or time down is half the total time. And I know that acceleration is change in vertical velocity over time, so time is change in vertical velocity over acceleration. Once again, at the tippy top, my vertical velocity is 0. So the change in vertical velocity until you get to the tippy top is 20 meters per second divided by the acceleration. So it says it takes 2.04 seconds to get to the top, another 2.04 seconds to fall down, total of 4.08 seconds. Once I know my total time, I multiply it by the horizontal speed to get the horizontal distance, and then I can use this equation and half the total time, just the falling time, to find the maximum height. Once again, it's 20.4 meters tall. You can always use 10 meters per second squared instead of 9.8. That would round things off a little bit. So no worries with that. Hopefully that's helpful.